Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be starting on another background topic which will eventually help us to understand the rigid body dynamics in moving frames. Namely, we will be looking at the tensor algebra or the mathematics part of these, of the mechanics of these bodies. Okay, so tensor algebra. So we will talk about the so-called inertia tensor. So the key concepts are the tensor algebra we'll be covering. The second is the inertia tensor. And then we will be talking about the principal axis. We will be looking at some results which will help us to quickly find the principal axis, and then we will also look at the principal moments of inertia. Okay, so then let us look at the case of orthogonal transformation. Okay, so what have we got? So let us say so orthogonal transformation, as the name suggests, they each of the component vectors are perpendicular. Well, that is, if we take the dot product, then the dot product of these basis vectors in these frames are going to give us Kronecker delta function. So let us say we have two frames. So let us say we have C frame, which is O x1, x2, x3. Let me just show that. So this is x1 E1 frame and x2 E2 frame, and the final is the x3 or the E3 frame. So x1, x2, x3, and then we look at another frame C prime given by O x1 prime, x2 prime, x3 prime. So again, we can draw a similar diagram as this, with the the axis being represented by the primes. And then we can talk about these EIs, these E1, E2, E3. These are the unit vectors. So this and this, E1, E2, E3, these are the unit vectors. And let us have V be the expanded form. So let us consider a vector V. So V is a vector, right? So vector V is, we can write it as V1 E1 plus V2 E2 plus V3 E3, and this is also equal to V1 prime E1 prime plus V2 prime E2 prime plus V3 prime E3 prime. Right, and if we take look at the same vector, well, if we look at the individual components of this vector, so Vj prime, the individual components, that is these. So Vj prime can be found out by taking a dot product of this vector with the corresponding unit vector Ej prime. Right, so we have Ej prime with E1 times V1 plus Ej prime E2 with V2 plus Ej prime E3 with V3, right? And we can now rewrite our transformation matrix A going from C to C prime, right? We can see that the Vj can be represented by these elements Ej dot E1, Ej dot E2 and so on. So all the three, so now since J is between 1 to 3, we can now write the three rows of the matrix, which will be of the form E1 prime with E1, E1 prime with E2, E1 prime with E3, right? And so on. We have E2 prime with E1 and so on. We can write all these elements, and this is our transformation matrix from one to the other. We can quickly now, so what we see here is that from here we see that any vector v in the coordinate frame C can be written as A transpose times V prime. A transpose times V prime, where V prime is this quantity here, right? And then or my V prime is A transpose, so V prime is A transpose AV. So that's my V prime. So that's A transpose AV. So we see that V is related to V itself, which means that this quantity A transpose A has to be identity. Or we get another concept, or the so-called A transpose A, which is A transpose being identity, which means that our matrix of coordinate transformation has to be a unitary matrix. A unitary matrix. A unitary matrix. Okay. So then what we have is, let us look at some examples of this matrix of coordinate transformation. So some examples are the case of rotational and reflectional transformations. So rotated and reflected coordinate systems. Okay, so suppose C prime is going to be obtained by C, let us say through a rotation about one axis. So let me draw the axis here. So this is my x1, x2 and x3, and this is my center O. So C prime is obtained through C by rotation through an angle, angle psi about OX3, right? So if we start to find out all these terms in the transformation matrix E1 prime E1, E1 prime E2, we see that let us try and draw this figure, so that might be easier for us. So we have the E1 x1 prime axis. So this is x2 prime. So this is psi and this is psi, and that's it. So what we get is that E1 prime with E1 is cos psi, and E2 prime with E1 is minus sin psi, and E3 prime E1 is 0, and E1 prime E2 is sin psi, E2 prime E2 is cos psi, and E3 prime E2 is 0, right? So we can take all these inner products here, all these terms will come out, and similarly we can check, since the OX3 axis is not going to change with this planar rotation, we see that E1 prime E3 is E2 prime E3, this is equal to 0, and E3 prime with E3 is 1 because the E3 axis never changes. So now compiling all this information in the form of a matrix, we see that the rotation matrix about the E3 axis will be cos psi sin psi 0 minus sin psi cos psi 0 0 0 1. And similarly, we can write down the transformation matrices for rotation about the OX1 axis. So similarly, or the rotation about OX2 axis and so on. Okay, so let us do a quick example. The example that I have is, the problem says a coordinate C prime is obtained by rotating the coordinate C through an angle of 30 degrees about OX1. Right? So find the transformation matrix. A double bar between C and C prime. Right? So a vector V has, now this is the second part of the problem. A vector V has components 3, minus 1, 2 in C. Right? So we want to find what are its components in C prime. Okay. So first let us try and write down the transformation matrix between C and C prime. So the rotation is about the OX1 axis. So the OX1 axis will not change. So our matrix A will be 1 0 0 0 0 and then cos psi sin psi minus sin psi cos psi. Right? And this is at we have to evaluate at psi equal to 30 degrees. And once we do that, we will find, so this is 0 0 square root 3 by 2 1 by 2 minus 1 by 2 square root 3 by 2. So if we find what is this vector V prime, so V prime is now A dot V. So our V is 3 minus 1 2, and we take the multiplication, we get the following result, and that should be a fairly simple problem. Okay, so then I want to write down the rotation matrix for the general rotation, not just rotation about one of the 3 coordinate axes. So let us say we are rotating one frame to the other with respect to a general vector. So in general case, we see that the rotation of C takes place about the axis O, n, right, where n is the unit vector. Right? So we have that A is in this case going to be cos of psi plus 1 minus cos psi n1 square, 1 minus cos psi n1 n2 minus n3 sin psi, 1 minus cos psi n1 n3 plus n2 sin psi. So this is the general formula about the rotation about any vector n with components n1, n2, n3. The other set of components is 1 minus cos psi n1, n2 plus n3 sin psi plus the second component is cos psi plus 1 minus cos psi this is n2 square, and then this is 1 minus cos psi n2 n3 minus n1 sin psi. And then the last set of three components are 1 minus cos psi n1 n3 minus n2 sin psi. And then similarly we can repeat by permutation of n1 n3, so it will be n2 n3, the same factor repeats, minus n1 sin psi, and then finally the last term is cos of psi plus 1 minus cos psi times n3 square. Okay, so this is the general rotation matrix. We have some examples. I think we can, I can quickly show the example, but we may not solve it right away. But the solution method is easy. So the problem says that the coordinate transformation from C to C prime through an angle of 60 degrees about the axis OP, where P is the point with coordinates 1, 1, minus 1 in C. Right? So find the transformation matrix A between C and C prime. So a vector V has components 3, minus 6, 9 in C prime, and we have to find the components in C. Okay, so we see that the new matrix is obtained by rotating about this point with coordinate 1, 1, minus 1. So the corresponding unit vector will be 1, 1, minus 1 by its norm, which is square root 3. So then if we plug these values in this transformation matrix, we will get the result, and then we have to find what is V in the next part. Says what is the vector V. It is given that vector V prime has components this. So this is the component of the vector V in C prime. So we are given what is V prime, and if we multiply it with A transpose, we are going to get V, because V prime is A times V. Right? Okay, so then similarly, let us talk about the operation of reflection. So reflection will be, let's say when we are talking about a reflection of a coordinate axis, it is with respect to a plane. So let's say we are drawing a coordinate axis again. So x1, x2, x3, and we are reflecting about the xy plane, the OX1, OX2 axis. So if we are reflecting about the x1, x2 plane, then we expect that x3 will be replaced by minus x3 and x1, x2 remains as it is. Right? So suppose C is reflected to C prime, is reflected in the OX1, x2 plane, then the transformation matrix A is 1, 0, 0 and 0, 0, minus 1. Right? And we see that now, so x3 becomes minus x3. So let me write down the general matrix of transformation for reflection. So what we see is A for the general case comes out to be, so this is for along any along the along the any plane whose which is perpendicular to the vector n, right? So this is along a vector n with components n1, n2, n3, right? So we get the matrix is 2 1 minus 2n square minus 2n1 n2 minus 2n1 n3 minus 2n1 n2 1 minus 2n2 square minus 2n2 n3 minus 2n1 n3 minus 2 n3 n1. So minus 2 n3 square, right? So we have that n comes out to be, well, so this is what we have. Okay, so then we have some quick examples. So let me see this example. The problem says we have a coordinate system C prime obtained by reflecting C in the plane x3 2x1 plus 2x2, right? So let us so we find the transformation A between C and C prime, and we also find the transformation matrix when C prime is obtained from C, right, by performing the above reflection, by performing the reflection above, followed by rotation of 90 degrees about the x3 axis. Okay, so we see that we have first a reflection about this plane. So this plane can be written as 2x1 plus 2x2 minus x3 is equal to 0. So in this plane we have the direction cosines as 2 comma 2 comma minus 1, and if we divide it by its magnitude it will be 3. So 2 comma 2 by 3 comma 2 by 3 comma minus 1 by 3, and we see that in this case we have that A is going to be if we plug this, so this is our vector n along which the reflection is happening, and if we plug it in our matrix A, we will get the matrix, and then the matrix A in this case comes out to be people can quickly find out, so it's fairly easy by plugging in the value of n here. The important thing I wanted to mention is that there is a second operation which is mentioned in the problem. It says that a matrix C prime is obtained from C by performing the reflection above, which means above, followed by the rotation of 90 degrees about the x3 axis. So now let us see what is this rotation matrix, which is 90 degrees. So it is rotation of x3 axis by 90 degrees, right? So x2, x1. Right, so we are performing a rotation of 90 degrees about the x3 axis. So we see that x1 becomes x2. So if we were to write this matrix of transformation, so in the first row which is for x1, it becomes x2. So 0, 1, 0, so x2. But x2 now goes to negative, right? So x2 becomes, it becomes negative x1. Right, so what we have is x1 becomes x1 becomes x2 and x2 becomes, well, x1 becomes x2 and x2 becomes negative x1. So x2 becomes, well, 90 degrees rotation, so it becomes x2 and oh, so x2 becomes negative x1 here. So this is our new x2 prime axis and the new x1 prime axis is here. So x2 becomes negative x1 and x3 becomes 0, 0, 1, right? And then, so this is what we have. So then let us now, so our final matrix of transformation will be B times A, where A is our matrix, our reflection matrix, and B is our rotation matrix, and the product of these two will be the answer. Okay, so then typically I want to highlight that whenever we talk about transformation matrices, these are all unitary matrices. So transformation matrices are unitary matrices, which means that A transpose A is identity, or if we find the determinant of this A transpose A, this will be plus 1 or minus 1. And for a right-handed coordinate system, we see that the rotation matrices have determinant 1, have 1. Okay. We take the positive sign. So, in this module I am all out of time, and in the next module we will be talking about the concept of tensors, well, starting with scalars and vectors. So thank you so far for listening.